Hey everyone, and welcome back to AI.Code.Cast. Today we're diving deep into a classic coding problem that you've probably seen in coding challenges or maybe even in some real-world scenarios.
Yeah, this one's a good one.
It is. All right, so imagine you have a sorted array. It sounds simple enough, right?
Sure.
But here's the twist. Every element in that array appears twice, except for one sneaky little element.
Uh-huh.
So how do we find that unique element? And more importantly, how do we do it efficiently?
Efficiency. That's the key, right? Because if we have a small array, no big deal. We can just look through it.
Right. Brute force it.
But what if we're talking about an array with millions or even billions of elements?
Exactly. That's where things get a bit more challenging, and that's where clever algorithms come in to save the day.
Absolutely. And in this case, there's a really elegant solution using binary search.
Binary search? Interesting. I usually think of binary search when I need to find a specific value in a sorted array.
Right. You're probably used to the, is it bigger or smaller kind of binary search?
Exactly. But here, we don't even know the value of the unique element. How can binary search help us?
Well, it's all about recognizing the patterns and invariants in this problem.
And variance.
Yeah, like something that always holds true. So in this case, we know that every element except one appears twice right.
Right.
That means that if we look at any subarray, the parity of its length.
Parity, meaning whether it has an even or odd number of elements.
Exactly. That parity tells us something about whether or not the unique element is in that subarray.
Okay, I think I'm starting to follow this.
Yeah.
So how does this parity idea help us use binary search?
Well, instead of comparing the middle element to a target value like we normally do in binary search, we're going to be comparing the middle element to its neighbor.
Okay. And are we looking to see if they match or not?
Exactly. That's the key. If they match, we know something really important about where the unique element can't be.
I'm guessing it can't be in that half of the array since the unique element doesn't have a twin.
You got it. So we can discard that entire half and focus our search on the other half.
That's clever. So we're not comparing values directly. We're using the parity of the subarray lengths to guide our search. We're narrowing it down based on whether those middle elements are twins or not.
Precisely.
This is pretty cool. So are we ready to walk through an example to see how this works in practice?
Let's do it.
Okay, so let's say our sorted array is 1, 1, 4, 4, 5, 5, 6, 6, 8, 9, 9. And remember, our goal is to find that unique element, the one that doesn't have a twin. In this case, it's the number 8.
All right, so let's walk through our binary search algorithm step by step using this example.
Sounds good. Where do we begin?
Well, just like in a regular binary search, we start by initializing 2 pointers, low and high.
Low and high. Okay.
Yeah.
And these mark the start and end of our search space, right?
Exactly. So initially, low would be at index 0, the very beginning of the array, and high would be at index 10, the very end.
All right, so we've got our boundary set. What's next?
Now we need to find the middle index, which we'll call mid. We do this by averaging low and high.
Yeah.
So in this case, 0 plus 10 divided by 2 gives us 5.
So mid is pointing to the element 5 in our array.
Right. Now here's where we use that parity check we talked about. We need to make sure that mid is always pointing to an even index.
Right, because we need mid to potentially be the starting point of a pair.
Exactly. In this case, we're in luck because 5 is already an even index.
Perfect. So now what do we do with our mid?
We compare the element at mid with its neighbor, the element at mid plus 1. So we're comparing the 5 at index 5 with the other 5 at index 6.
And they match.
They do. What does that tell us?
Well, if those two 5s match, it means our unique element can't be anywhere in that left half of the array.
Exactly. Because if the unique element were there, it would disrupt that pairing.
So we can safely discard the entire left half up to and including those two 5s.
Exactly. We do that by moving our low pointer. Where would you move low to?
Well, we want to move it past the matching pair, so I'd move low to mid plus 2, which would be index 7.
You got it. Now our search space has shrunk. Low is at index 7, and high is still at index 10.
Okay, time to calculate a new mid.
Exactly. Our new mid would be 7 plus 10 divided by 2, which gives us 8.5.
But wait a minute, we need mid to be an even index.
Right, so in this case, we'll round 8.5 down to 8.
So now mid is pointing to the element 8, which is actually our unique element. We found it.
We did, and it only took us 2 iterations. Of course, in the worst case scenario, we might have to keep having the search space a few more times.
But still, it's much faster than going through the array element by element, especially if it's really big.
Exactly. That's the power of binary search. Now, to make sure we really understand this, let's talk about how this might look in pseudocode.
Okay, yeah, pseudocode would be helpful. Walk me through it like you're giving me hints.
All right. So first, we'd initialize our pointers, low to 0 and high to the last index of the array.
Okay, so just like we did in our example.
Exactly. Then we'd have a loop. And what would be the condition for this loop to continue?
The loop should continue as long as we still have a search space, as long as low is less than high.
Right. Now, inside the loop, we would calculate our mid, just like we've been doing, averaging low and high.
And then making sure it's even. Right.
Absolutely. Next comes the core of our logic. What do we do if the elements at mid and mid plus 1 match?
Well, if they match, we move low to mid plus 2 to discard the left half.
Precisely. And if they don't match?
Then we must move high to mid. Right. To focus on the left half, but keep the element at mid in play.
You got it. And finally, when the loop ends, meaning low and high have met, we've found our unique element.
So simple, yet so powerful. But I'm curious, is this the only way to solve this problem? Are there other clever tricks we could use?
There's almost always more than one way to solve a problem. And in this case, there's another very interesting approach that uses a bitwise operator called XOR.
XR. I've heard of that. Tell me more. Okay, XOR. Refresh my memory. What exactly is XOR again?
So XOR stands for exclusive OR, and it's a bitwise operator, meaning it works on the level of individual bits.
Right, bits, the zeros and ones.
Exactly. An XOR basically gives us a 1 as output only when the corresponding bits in the two inputs are different.
So like 1 XOR 0 would be 1, but 1 XOR 1 would be 0.
You got it. If the bits are the same, the output is 0. If they're different, the output is 1.
Okay, I remember now. But how on earth does this help us find a unique element in an array?
Well, XOR has this really cool property where if you XOR any number with itself, the result is always 0.
Oh, that makes sense. Because all the bits would be the same, so the XOR would always produce 0.
Exactly. And that's the key to solving this problem using XOR. Remember how every element in our array appears twice except for the unique one?
Right.
So if we XOR all the elements of the array together, all those pairs will essentially cancel each other out, leaving us with just the unique element.
Ah, I see. It's like those matching elements just disappear in a puff of logic.
I like that. A puff of logic. So let's go back to our example array. 1, 1, 4, 4, 5, 5, 6, 6, 8, 9, 9. Let's pretend we're walking through the array and XORing each element into a variable called, say, result.
Okay, so result starts as 0.
Right. And we take the first element, 1, and XOR it with result. So 1 XOR 0 is 1.
So now result is 1.
Right. Then we move on to the next element, which is also a 1. We XOR that with result.
So 1 XOR 1, which is 0, back to 0 again.
Exactly. They've canceled each other out. And this pattern continues as we go through the array.
The 4s cancel each other out, the 5s cancel, the 6s cancel, the 9s cancel.
Right. And we're eventually left with just the 8, our unique element, sitting in the result variable.
That's pretty amazing. So
Yeah.
basically all the pairs self-destruct through the power of XOR. I love it. But is this approach as efficient as the binary search method?
It's very efficient. With XOR, we only need to go through the array once, so it has a time complexity of O(n).
Oh, wow.
And it uses a constant amount of extra space, just that result variable, so the space complexity is O(1).
Very cool. So we've got two great ways to find our unique element. The modified binary search, which is super fast because it keeps having the search space, and this really clever XOR approach, which cancels out the pairs.
Exactly. And both solutions highlight important concepts like understanding patterns in our data and thinking about efficiency in terms of time and space complexity.
Totally. These are skills that can be applied to so many different coding problems. It's not just about memorizing solutions, it's about learning how to think like a problem solver.
I couldn't have said it better myself.
Well, thanks for guiding me through this deep dive. It's been a lot of fun and I've learned so much.
My pleasure. Always happy to chat about code.
And to all our listeners out there, keep practicing those coding challenges and don't be afraid to explore different approaches. You never know what clever solutions you might come up with. Until next time, happy coding, everyone.